Okay, good morning, everyone. So I'm Xueqing Lü, and I'm presenting the PhD work today done by me and my supervisor, Dr. Stephen Davis. So this idea actually comes from my master's project. So in my master's, what I did was to test the effect of salient sidereal sound and some visual hints such as co-workers to people's safety decisions. And as we can see that we have a worker warning people not to go through a dangerous space, and we have the barriers around, and some co-workers using a safe route. So the layout of this environment was we have a shorter unsafe route and a longer safe route, and we want to see whether people take the shortcut. And what we found out was that salient sound can help people to create a sense of normality when there is the related visual assets, and people do learn from mistakes. But at the same time, we still don't know what's the underlying reason how people learn. For example, we find that people look at the hints, but their behaviors were not changed based on those hints. So we're thinking, do they really see the hints, or they just look at the direction of the hints? So that's why we decided to use eye tracking headset and EEG device to measure people's attention. So the FOV is the eye tracking headset. It's got cameras inside to measure people's gaze point, and it's got a built-in Unity package. So on the picture on the right, there's the green dot representing people's gaze point. So to avoid people guess the reason that why we use the eye tracking headset, we actually make an interactive function. So there's the hint button on the blackboard. When people are looking at the hint button and press another button on the controller, they will activate the hint. And the hint is an NPC telling them where the item they need to collect is. So the reason that we want to have this hint is to make sure that people work on the routes that we design. So they walk to the NPC, and the NPC mark the item they need to collect on the map for them. So in between the NPC and the item, there's the hazard. And the EEG gives us attention, meditation, and the combination of these two. And at the same time, we get different bandwidth, 8 different bandwidths of brainwaves. In this study, we're looking at attention and alpha wave, which is related to problem solving and learning. We did a pilot study on 6 PhD students in the School of Civil and Environmental Engineering in UNSW, and there were 10 items to collect to build a scaffold, but only 1 student finished the whole tasks wearing the VR headset, and the other 5 felt pretty strong VR sickness. And that student who finished all the tasks actually had 2 years first-person game experience. So that's the point how they can reduce the sickness. So after that, we decided to split the 10 tasks into 2 sessions, half of them using laptop and the other half using VR headset to reduce the exposure time in VR headset. And at the same time, we can compare the people's safety decisions with the 2 displays. And we invite students, telling them we want people who don't have motion sickness or VR sickness, which has similar symptoms. And because in our environment, we can actually use things like teleport, because they may just skip the hazards. And what we do to reduce the sickness is to change the way to turn. So before we use the thumbstick, when people push the thumbstick, they just keep turning. And now we change it to turn 30 degrees when each time the thumbstick is pushed. And just a little suggestion that if you have to do something to make people stick, maybe prepare some tissue for them and water, because they may ask for water and they may sweat. So these are the 10 tasks. So they need to collect 10 items. And we put 8 hazards in it. The reason we don't put 10 hazards is we don't want people to intentionally look for hazards when they're doing the tasks. And in the 8 hazards, there are 4 of them above eye level, and the other 4 below or at eye level. Because in my master's project, we put 2 hazards, one above eye level and another on the ground. And we found it might be that the hazards above eye level are harder to identify. And we add different hints to the hazards, like sound of the engine, barriers, flashing light, warning signs, and some dust or verbal warning from the co-workers. So here is a video of the test environment. Before they start their task, there is a safety manager asking them to wear the personal protection equipment. That's a hint for them to realize that they need to care about their safety. Then they go to this quest system, which is a blackboard, and activate the quest. We have text on the left and image on the right. Then I click on the button and try to find the NPC called Tom. The NPC marked the item on the map for them. Then they go and find the item. The hazard that they are passing is the electrical cables in water. So we can see that when they're collecting the item, they are actually still checking the cables around. And we thought that when we add hints, people actually can identify more hazards and avoid the injury more. But actually, except for warning signs and beeping sound, all the other hints reduce the chance of hints being identified. Let's just think of a real-world scenario. If we're on the way to meet a friend, and we pass a roadwork, and there's barriers around, do you really stop and think of what's the hazard? Where do we just walk around? Maybe that's what happened in this environment. And then we compare the hazard identification and injury rates for the hazards above eye level and at or below eye level. So the hazards above eye level are less likely to be identified and injure people more. And we compare the 2 types of displays. So people injure more times with laptop than with headset display. And after they injure the first time, are they willing to injure them another time using the shortcut or find another way? So when they're using the laptop display, they are still think they are playing a game. So they will injure them more times after. And from the EEG data, we can find that the average attention level is higher when they're heading to the blackboard, and the alpha wave is higher when they're heading to the blackboard, heading to NPC, and when they're injured. But that's just the average level, and we know that brain's activity actually happens pretty fast. So these activities usually last for 1 minute. And now we need to look at the details of what's happening. So here is a video. We do a screenshot, screen filming for the game they're playing, and at the same time we record the brainwave. So in this part, the red line is the attention, and this one is meditation, which is the green line. And there's the delta, theta, low alpha, and high alpha wave. So start from when I first get to the entrance of the site. And now they're looking at the map, try to find where the blackboard is. So during the time when they're trying to figure out where the blackboard is, their attention increases. And now they prepare to get ready to press on the buttons, look for the quest. Here I cut a little bit because this participant actually thought this guy is James. So during the walk to this NPC, the brainwave is pretty stable until they see the NPC waving at them and they are focusing on the NPC.
I marked it on the map for you.
And now they see the shadow of the trench box. So they're walking around and they look at the trench box. And when they put up the map again and try to figure out where the blackboard is, their attention increases again. I think this video is pretty long, so we jump to the end a bit. When they get injured, and looking for what's happening, their attention increases. Here, the attention is almost zero. I guess they're just willing to use the shortcut and injure them again. And he pull up the map again, try to figure out where the blackboard is. The attention goes up again. So we can see that during the wayfinding process and when they're injured and trying to figure out what's happening, their attention actually goes up. And the findings from this experiment. So unfortunately, we haven't got enough participants so far because the time that I do the experiment is actually exam period, so we can't get enough students. And based on the sample size, 18 students, 10 in the control group without hints, and 8 in the experimental group with hints, we find out that except for warning signs and beeping sounds, all the other hints reduce the chance of hints being identified. Hazards being identified. And when the alternative route is more accessible, people would change their unsafe behavior earlier. So in the scenario that we saw when the participant was injured, that's at one entrance of the building, and the other entrance is all the way across. So they have to decide whether to injure themselves again or use the longer route. But for the other hazards, like if the hazard is here and it's a pretty open area, they just walk around. And the hazards above eye level are less likely to be identified. Hazards above eye level injure people more, and people are less willing to injure themselves when wearing the headset than using the laptop. And people's attention level and alpha wave are higher during wayfinding and injuries. So based on this, our future study will first expand the sample size, and then we'll compare the visual hints such as barriers, warning signs, and flashing lights. Then we compare the audio hints, like verbal warning telling the hazards, verbal warning with not telling the hazards, and beeping sound. And we'll compare good and bad hints, such as when their coworkers are doing things unsafely, they will injure, or they will be lucky and not injured. So do they copy their coworkers' behaviors? And then we'll compare the training effectiveness of video, VR, and MR. Okay, that's all. Thank you for listening, and any questions?